This is the Master Brewers Podcast, brought to you by the Master Brewers Association of the Americas, a volunteer organization dedicated to continually improving the products and processes of our membership since 1887.
Let's go!
Master Brewers brings you interviews with the industry's best and brightest in brewing science, technology, and operations.
Calm down, I'm moving too fast.
Support for this podcast and the following messages come from our friends at the Paul Mueller Company and Hopsteiner. Please thank them. This podcast wouldn't be possible without their generous support.
Paul Mueller Company has been manufacturing quality brewing equipment since 1964. Our innovative design and engineering will save you time, labor, and ingredients, sending money back to your bottom line. Learn more about our new mobile hop module at paulmueller.com. This Master Brewers podcast is proudly sponsored by Hopsteiner, a global leader in the hop industry focused on quality, sustainability, and innovation in new hop varieties and hop products. Contact our brewery sales team to provide you with the hop-related tools you need to craft your next great beer. For more information, visit hopsteiner.com.
Low pressure freeze controls shutting off, oil failure issues on a compressor, flow issues inside of the facility. A lot of times that can all get routed back to just the glycol concentration not being adequate inside the reservoir.
This week on the show, how your chiller system works, troubleshooting tips, common mistakes, and easy preventative maintenance to keep it running for years to come. Here's our guest.
Hi, my name's Damon Reed with Pro Refrigeration.
All right, Damon, there's a lot of confusing terms in refrigeration. Let's talk about BTUs, tons, and horsepower.
Yeah, so a BTU, the definition of a BTU is a British thermal unit. And that is the amount of heat that it takes to raise 1 pound of water by 1 degree Fahrenheit. That takes 1 BTU. So when we measure refrigeration capacity or cooling capacity of a chiller system, we oftentimes refer to it in BTUs per hour of cooling capability. There can be some cross confusion between BTUs and horsepower, mainly because with refrigeration, it originated in the air conditioning industry, and as the which operates at a higher temperature range. So what that means is with a higher temperature range, the compressor capacity is higher than it will be at a lower temperature.
Can you give us some examples?
Yeah, so at 28 degrees, which is our typical operating range for a brewery, a 5 horsepower compressor is going to generate about 38,000 BTUs per hour. That same compressor, if we raise the temperature and operate at 45 degree leaving fluid temperature, we're going to get close to 60,000 BTUs per hour of capacity out of that same system.
Yeah, so quite a bit of difference there.
There is, and I think in the air conditioning world, there's a lot of carryover between compressor horsepower to tonnage and BTUs, and it can be the definition of 1 ton of refrigeration is 12,000 BTUs per hour. So if we take the capacity of a unit at 50,000 BTUs per hour, divide it by 12,000, that's going to give us roughly 5 tons of cooling capacity. And on a 5 horsepower unit, it would carry over, or be very close to carrying over to the same horsepower range. Not going to be the same as we operate at lower temperature ranges.
How about giving us the 30,000 foot overview of sort of how a chiller system works?
So the way a system works, or a chiller system operates, is we're taking our mechanical refrigeration circuit and we are cooling a reservoir filled with propylene glycol and water. And the propylene glycol mixture is in the water to work as an antifreeze. The reason we need the antifreeze is because we're supplying that fluid into the brewery at 28 degrees Fahrenheit, it's picking up the heat from the fermentation vessels, from wort heat exchanger, potentially a cold room, and bright tanks, and we're bringing that back into the reservoir at a higher temperature. Then we take that fluid, move it through the refrigeration circuitry, which is going to have to operate at a lower, even lower temperature than what we're trying to achieve, typically by around 5 to 10 degrees Fahrenheit. So if we're trying to make 28 degree glycol, we're going to have to run the refrigeration circuit at probably close to 20 degrees Fahrenheit. And that's the goal with the glycol, is to prevent that from freezing on the refrigeration circuit.
Yeah, that's an important point, because I bet a lot of folks think, well, hey, I just need freeze protection down to my set point of 28 or whatever that is. But really, you need much more freeze protection than that.
That is correct. Yeah, we have to be able to transfer heat from one media to another. We have to operate with a temperature difference.
All right. Well, let's dive into that refrigeration circuit. I've seen you use your circle of cool to describe the process at district meetings, but I'm not sure where in that circle you'd like to start.
Okay, so on every refrigeration system, we break it down to, there's 5 major components that are in every system. It's usually easiest to start with the compressor. So what the compressor's job in a system is, it's a pump. It's a way of moving the refrigerant between the different devices that are in the system. The other component is our condenser, and the condenser can be either air-cooled or water-cooled. Most of the time we see that it's air-cooled. And if you were looking at a chiller system, that would be the device that has all the aluminum fins with copper tubes running through it. So its job is it dissipates the heat that's been picked up on the refrigerant and from the brewery, as well as the heat that we picked up from the compressor, and it dissipates that heat out of the refrigerant. Then it moves the refrigerant to the metering device. And the metering device is a component that it basically regulates the refrigerant flow through the system. So we have a big pressure change at the metering device. And then the refrigerant enters the evaporator, and the evaporator is where we get the cooling to happen between the refrigerant and the glycol. And there's separation between those. There's no mixing whatsoever. So they're separated by either stainless steel plates or copper tubing. As the refrigerant enters the evaporator, it boils off, and as it goes through a phase change, it absorbs heat from the glycol, and then it carries that heat back to the compressor. So those mechanically are the 4 components, and the 5th major component is the refrigerant itself. So the refrigerant, we can make adjustments to systems to utilize different types of refrigerants to be able to get different operating parameters. And so it's important to consider the refrigerant in the system, because some refrigerants they operate better at higher temperatures, and some refrigerants operate better at lower temperatures.
Do you want to talk about in a little more detail sort of how that refrigerant, as it goes through that circle, how it changes phase and temperature?
Yeah, so if we take, for example, the refrigerant status between the compressor and the condenser, coming out of the compressor, refrigerant temperature is going to be very high. And by high, it could be anywhere from 160 to 190 degrees Fahrenheit. And it's also going to be a vapor. We call that a superheated vapor. Then that refrigerant, as it goes through the condenser, it starts to transition as we remove some of the heat and take the temperature down. We'll get the temperature down in a condenser to around 100 degrees Fahrenheit, but it also changes state from a vapor to a liquid. But the pressure of the refrigerant hasn't changed. So we'll maintain pressure. We're just playing with the temperature and the state of the refrigerant itself. So then coming out of the condenser, I refer to it as a warm liquid, but it's technically a subcooled liquid. And that liquid refrigerant then enters the metering device. And at the inlet of the metering device, it will be let's say 100 degrees Fahrenheit. As soon as we exit the metering device, it starts to change temperature very rapidly, and we could be down around 15, 20 degrees Fahrenheit leaving it, but also the refrigerant pressure changes. You'll see anywhere from 40 to 50 psi pressure leaving the metering device. The metering device is usually going to be close coupled, meaning very close, not a lot of piping in between the metering device and the evaporator. And that's because as soon as we leave the metering device, we're starting our cooling process. So we want to keep all that cooling process inside the evaporator. So we go through the evaporator, the refrigerant, now it had some vapor and some liquid mix. By the time we leave the evaporator, we want purely a cold vapor. And that cold vapor could be anywhere from 30 to 40 degrees Fahrenheit, but it maintains that 40 to 50 psi pressure. We come into the refrigerant compressor, cool down the motor. The compressor starts compressing the refrigerant and moving it back into the condenser. It's just a constant cycle.
Very good. Okay, I guess let's get into, you've got some great images and descriptions of sort of the different components, which would be very useful to someone who wants to learn more, and we're going to link to those in the episode description. But in the meantime, let's proceed on and talk about some of the preventative maintenance issues that are common in chiller systems. I know you get asked this all the time, but how do you respond to brewers when they ask you how long their chiller is going to last?
Well, everybody wants to design and build for long-term use. The refrigeration system and the chiller system it's mechanical equipment. So if it's maintained and taken care of, it could last a very long time. I have seen systems that were 20 plus years old. But if systems aren't on a regular routine preventative maintenance, I have seen systems only last 5 to 10 years and then start having a lot of service issues. So we have a preventative maintenance schedule that we recommend, and all manufacturers will have something along this line. But down to daily, weekly, monthly, and semi-annually preventative maintenance procedures. Okay, well, let's go through some of that. What are some of the things that you guys recommend doing on a monthly basis? So on a monthly basis, the top items that we would recommend checking, what I'll do is go through these items, and then we can discuss them in more detail. But each unit, at a very minimum, I would check my condensers, mainly if it's an air-cooled condenser. Make sure that it's clear of any obstruction. Make notes of your glycol temperatures. Check for any audible visual alarms, and also take a note of your actual glycol fluid level. At the same time, another good thing to check is with using a glycol refractometer. Take a measurement of your glycol concentration and make sure that the antifreeze properties are still holding up. Those having those items documented, the temperatures, the fluid level, the glycol concentration, having those set up on some sort of a note database, even if it's just a spreadsheet that you maintain, it'll help give you some insight into potential issues coming down the road. Let's take a deeper dive into some of those. So when you say that you're checking the condenser for obstructions, what kind of stuff are we looking for there? So you would see things like this time of the year, or in the spring, if you're in an area where they have a lot of cottonwood trees. After cottonwood season, you could see a lot of impacted cottonwoods sticking to your condenser surface. I've seen things like plastic shopping bags that have floated around, any debris, construction debris, particularly after a new installation. Plastic, things like that could get up and they'll get sucked up and on the condenser surface. So as the fan's trying to move the air across that condenser, it's going to bring in anything that's floating around in the air into that surface area.
And obviously, checking the reservoir level is probably pretty self-explanatory. How often do you see a change in glycol concentration rear its head like that?
Well, I have seen the glycol concentration maybe over the course of a 1 year to 2 years, where you'll slowly start to see a breakdown on the fluid level. You might see a change in freeze concentration of a half a degree Fahrenheit over the course of 1 to 2 years. There's been instances where on initial commissioning, the fluid reservoir it drops as fermenters are brought online, and sometimes we just forget to top up that reservoir.
Coming up.
If you feel like you need to start dropping your set point below 28 degrees Fahrenheit, start maybe looking into what other items could be happening as far as flow rate.
I'm John Bryce, and you're listening to the Master Brewers Podcast from the Master Brewers Association of the Americas. Here's what's coming up on the Master Brewers calendar. District Pittsburgh meets at Piper's Pub June 4th. District Midwest meets at 7th Sun Brewing in Columbus June 9th. District New York meets at Anheuser-Busch in Newark June 14th. District Philly's annual golf outing is June 15th. The annual District Texas Summer Meeting is the weekend of August 3rd in Kerrville. Registration is now open for the ASBC MBAA Brewing Summit, which takes place in San Diego this August. Register at mbaa.com, where you can also view the full calendar of events with more details or find a district meeting near you. Now back to the show. Damon, you want to talk a little bit about the various tools for verifying freeze concentration?
Yeah, so you could use a hydrometer and get a gravity reading, and there's some charts available online, and we have them on our website as well. But you're looking for a freeze point concentration on your fluid to be at least 20 degrees below your set point, or whatever your coldest ambient temperature is going to be. It's important to consider your ambient temperature, because if for some reason you have pumps off, you have a power failure, that fluid needs to be protected to those temperatures. So at about 0 degrees Fahrenheit freeze point, we're looking for a gravity reading of about 1.035. If you can get a glycol refractometer, it'll actually give you a reading in degrees Fahrenheit for what your freeze point is. So that makes it real easy to take a sample, and you don't have to worry about conversions. You don't have to worry about calibrated temperatures. I know a lot of times the fluid samples that are taken need to be warmed up to 70 degrees Fahrenheit before the reading is taken, so that the calibration is correct. With a glycol refractometer, you just take a small drip sample of your fluid, put it on the window, and it tells you exactly what your freeze concentration is.
Okay. You also mentioned inspecting that refrigerant sight glass. What are we looking for there?
Yeah, so most systems are going to have a refrigerant sight glass that's about the size of a quarter, and sometimes they will have a plastic cover over the top of them. You can remove that plastic cover, and while the refrigeration circuit is running, you want to look in that sight glass, and you should not be able to tell if it is clear or if it's full or empty. It should just be solid clear. If you see bubbles moving through it, that's an indication that you could be low on charge. You could have something going on with refrigerant level in the system. You could have a glycol concentration issue. It's probably a good time to call for tech support or call in a mechanical contractor to inspect the circuit for you.
A few other things you mentioned to inspect things like the actual system set point and making sure that hasn't changed. It seems like a lot of people's inclination when they're not getting the cooling they need is to just bump the set point down further. But as you've indicated, all that does is decrease your system capacity in the end. So that's something to be aware of for sure. So why don't you let us know any other watch outs in terms of set point, and then also get into sort of inspecting the actual suction and discharge pressures.
Okay. The set point is something that is a lot of times we understand when we're using a chiller system that the lower we can make that temperature of the set point is going to give us a bigger temperature difference between what we're working with in the brewery. Like, for example, if we're trying to crash a tank from say 70 down to 32, I've had people ask, well, can I operate my set point at 20 degrees Fahrenheit as opposed to 28 degrees Fahrenheit to try and get a little faster pull down. And what we see is once you get glycol temperatures below 25 degrees Fahrenheit, you can start to build a layer of ice inside of like a bright tank, for example. Mainly once you start getting the beer temperature down close to 35 degrees Fahrenheit, all of a sudden everything will start to stall. And if you've ran your set point down below 28 degrees Fahrenheit, the odds are pretty high that you could have built some ice inside the jacket, and then you won't even be able to get below 35 degrees Fahrenheit, 34 degrees Fahrenheit. So when I'm working with somebody who wants to drop set point below 28 degrees Fahrenheit, usually what we start to look for is a flow issue of the glycol inside the facility. And there's usually on an installation, we'll have filtering that's in place on the supplier, the return header. And that is more often than not has built up some debris and has started to plug and impede the flow through the system. So that's from a set point standpoint. Those are the things that's the main item that I would keep an eye out for. If you feel like you need to start dropping your set point below 28 degrees Fahrenheit, start maybe looking into what other items could be happening as far as flow rate.
Okay. And then on the compressor suction and discharge pressures, I'm sure a lot of folks see the dials on their chillers and then say, hey, it's great that I have that information, but I have no idea where it should be. Could you give a little bit of advice in terms of kind of normal acceptable ranges for those pressures?
Yeah, the suction and discharge pressure ranges, they're going to be relative to the type of system you have, as well as the type of refrigerant that you have. For the most part, systems that are operating with refrigerant 404A, their suction pressure while operating, I would expect to see that anywhere from 35 to 45 psi. And on the discharge pressure, I would expect to see somewhere between 250 and 300 psi. The suction pressure and the discharge pressure will kind of work together, but the metering device kind of regulates that. And ambient temperature will have a pretty big role on your discharge pressure. So if it's 105 degree day and you're seeing your discharge pressures 300, maybe 325, you might just take into account that, well, it's pretty hot outside. I've checked my condenser. I know I'm getting good airflow. Let's come back and check it, in a few hours when the temperatures come down a little bit. There, on the suction pressure side of things, it should remain relatively stable throughout the refrigeration cycle.
You've also got another checklist for sort of quarterly preventative maintenance. So let's take a look at that.
Sure. So on a quarterly basis, I would take a look at systems. More so, this is where I would start to look at having somebody that's a qualified refrigeration mechanic or a contractor involved. Mainly because that's where I like to see things like amperages taken of my motors. By motors, I mean the refrigeration compressor, the circulation pump, the process pump, or the condenser fans. Electrical motors will trend over time. If you start seeing an increase, a gradual increase in amperage, that can point to issues with an electric motor. And if you start to see a gradual decrease on pumps in particular, that could mean that you're starting to get a blockage downstream, or it could be something going on with an impeller. The amperage readings can really tell you a lot. So if you were having a contractor come out and take those types of measurements for you, you could just request that they give you a report with those readings taken, and then store that somewhere safe where you could trend back to it and start to get some ideas of what's going on.
Nice. All right, let's cover some various watch outs. Why don't you talk a little bit about the type of glycol and water that should be put into these chiller systems?
Yeah, so when we get asked on the type of water to use in a system, generally tap water is going to be okay. And I say that because it matters what kind of propylene glycol you're going to operate with. You want to find a propylene glycol that has a inhibitor package incorporated into it, and that inhibitor package can offer protection against some water quality issues. The best scenario to operate with is to use deionized water in the system. That's gonna already have a solid water quality to it, that it won't be as critical with the inhibitor package to protect it, but the inhibitor package in the propylene glycol fluid is still important because of how it can protect the propylene glycol over the course of time.
I know you've mentioned in the past that you've seen some folks ruin chillers with power washers. Why don't you talk about that?
Yeah, so cleaning of the air-cooled condensers. So you could get impacted items on the front of the condenser, such as like cottonwood debris or any construction debris. If it's something that you could just grab and just pull away, you want to do that. I have a air conditioning system at home, and that come every June, it's completely full of cottonwood debris. So I will use my shop vac and just gently pull that cottonwood debris out. You don't want to spray water into it to try and rinse it off, because that could just impact the coil. And once that debris is packed into that fin surface, it can be really hard to remove. What I have seen people do before too is try and use a pressure washer, and the aluminum fins on the condenser, those are very delicate. And if a pressure washer or compressed air, anything with high pressure is used, you could bend those aluminum fins, and to the point where it's not going to be repairable. As those bend over, it impedes the airflow through the coil, and you've basically destroyed the coil.
I've seen some mechanical contractors recommend chemical cleaning of the coils. Do you want to talk about that?
Yeah, so with chemical cleaning, if you have to be very careful. Different municipalities will have different regulations in place. Some facilities don't, or some municipalities will not allow any type of chemical cleaning whatsoever. So they're corrosive. You really got to be careful with those types of chemicals. Typically, I'll see those being requested when there's been a lot of corrosion buildup or scaling on a system. Some areas where ambient temperatures, like Arizona, for example, Phoenix, Arizona, if they are trying to supplement the condenser capacity by using like a water misting system, that can lead to scale buildup on a condenser, and utilizing chemicals to remove that is one option. But there's a lot of safety concerns. I wouldn't recommend that anybody that's not got experience or training with those chemicals utilize them.
So scale is really the only instance in which you should need to use a chemical cleaner?
That is correct,
okay.
Yes.
All right. All right.
Yep.
So how about some of the more common problems you guys get on service calls? What's kind of at the top of your FAQ?
I think our top scenario is glycol concentration. We answer quite a few technical support calls where we just there'll be symptoms on the refrigeration system that point to a glycol concentration issue. Low pressure freeze controls shutting off. You could see oil failure issues on a compressor, flow issues inside of the facility. A lot of times that can all get routed back to just the glycol concentration not being adequate inside the reservoir.
All right. Any recommendations for spare parts that brewers should keep on hand to keep their chillers running?
Yeah, some of the spare parts, probably one of the most common things I would look at on any system is fuses. Inside of the electrical controls, are there any fuses that could be replaced? The lights, any of the indicator lights on the front of the control panels, those are good to keep on hand. One or two of those for replacement. I like thinking of spare parts, temperature sensors as well. If you've got any temperature sensor elements on your system, it might be good to have one of those hanging around. I probably wouldn't get into from the user's perspective of some of the deeper electrical components, because those are things that should be diagnosed by a qualified technician before they're replaced to identify what caused the failure. Fuses are something that if you have a voltage spike or something with your incoming power, you can replace the fuse, try it one time. If it blows the fuse again, call in a mechanic.
Yeah, I can't tell you how many times I've come in the day after a big thunderstorm or something, and having spare fuses got us back up and running right away.
Yeah, having fuses, and some of the fuses that can be used on the industrial refrigeration side of things, you might not be able to get easy access through like a Home Depot or Lowe's or something like that. You might have to go through a refrigeration or an electrical wholesaler.
That was Damon Reed here on the Master Brewers Podcast. If you want to see images for the refrigeration circuit, the circle of cool, or any of the system components we discussed today, type Damon, that's D-A-M-O-N, into the search bar at mbaa.com. The search results will return both slides from the presentation Damon gives at Master Brewers district meetings and a link to Damon's Master Brewers webinar, which can be viewed on demand 24/7. I'm really looking forward to the ASBC MBAA Brewing Summit coming up this August in San Diego. It only happens every 4 years, and it's not like any other conference you've attended. The Brewing Summit is 100% the science and technology of brewing. No pep rallies or business lectures, and you'll be surrounded by some of the smartest men and women in our industry. If you can only attend one conference in 2018, this should be it. Register now at mbaa.com.
That I should have mentioned, but I did. My fist full of courage, my heart full of rage. Well, I can't get stuck, I can't be losing too much, and then I'm heading out to any other place. My fist full of courage, my heart full of rage. Well, I can't get stuck, I can't be losing too much, and then I'm heading out to any other place. Calm down.